we talk about noise emission and how the noise can can affect the decision of the optimal trajectory for drones. But in reality, now we are going to see what we have developed inside RefMap in terms of the artificial intelligence, in particular deep reinforcement learning, to understand to predict the optimal trajectories that will also integrate the noise when it is ready, of course. So let's talk first about the background and motivation of our work. In fact, we can distinguish between two different steps. The first step consists on doing the DNS simulations in a very simplified human environment, here represented with two obstacles in line, and the second step is just to take the DNA simulations that are time variant. So this means that we have in every time step the velocity and the turbulence, an indicator of the turbulence in each position, and find the optimal trajectory by avoiding the most risky and dangerous region. So if you are more interested in the simulations, we published recently a paper describing what I'm talking about now. As you know, since we are interested in urban environment, we need to understand mainly the turbulent flows into urban areas, and we want to study a flow field in order to analyze the most hazardous regions around buildings, here represented as two buildings, and then we want to use this data to train and test the deep reinforcement learning algorithm. So just to understand the simulations, why these simulations are important, and why they are very, very expensive, because we are testing using, we are conducting some simulations using a software NEC 5000 that is based on spectral element methods. So this means that we are using a very coarse measures here. And you need many hours using a cluster to obtain these results. So I studied 3 cases with different gaps between the two buildings. As you can see here, namely skimming flow, wake interference, and isolated roughness, going from closest to the more distant obstacles, and here we have 2 obstacles with different heights. So we wanted to understand, when you have you are in a city, obviously the buildings are at different heights, so this can affect the most hazardous areas across the city. So we first analyzed the flow field. Here I represented some cases where we compare also the effect of the height of the building, but what we can understand from the comparison of these cases is that when we have 2 obstacles, the wake and so the space between the two obstacles is strongly affected, and we have very strong recirculation region characterized by this downwash. This means that when you have 2 obstacles, the flow behind the first building is pushing downwards, and this can also be interesting, because if you are flying with a drone right behind the first obstacle, you need to be very careful to not crash and touch the buildings. But if you increase the distance, then this effect is less important, and also if you have 2 buildings with the same height, obviously this effect is less important. So, but it is not the only quantity we need to understand. We also plotted the stresses and through kinetic energy here, and we can see that the most hazardous areas is at the top of the second obstacle and second building. That is quite intense when you increase the distance, but obviously it's less dangerous and risky, because here you don't have any obstacle to avoid, except for the fact that the energy that you need to exit this area, the circulation area, is increasing. Without defining many details about these cases, I would like to point attention on the decision-making process. Here we trained deep reinforcement learning recently published by our team, and this is an algorithm that combines PPO and LSTM, where PPO stands for proximal policy optimization, and LSTM is the long short-term memory network. This means that in our artificial intelligence, we also consider the history of the drones, obviously, because we are following the drones for all the steps all around buildings. Yeah. Okay. In the first step, that is still ongoing now, we only studied the 2D configuration, but the 3D case is ongoing. And here you have the cases that I already showed you for the mean velocity. Oh, it's not playing. Anyway, it was a video that you can show for each instant what is the flow field. But if we consider the drone, in this case we are using, for simplification, one drone that is considered as a mass point. No, yeah. Okay, is a mass point, and what we want to do is just training our neural network in order to give the direction to the drone, here represented by theta, phi, and d0, with theta and phi are the angles, relative angles of the UAV with respect to the direction to the target, and d0 is the distance to the target. So, as part of the deep reinforcement learning, we also have a total reward that is given by the sum of each rewards given by the steps. So, if the action gives me a step that for which the distance to the target is decreasing, so we have a positive reward. If I'm not touching anything, or I'm not touching the buildings, it's a positive reward, etc., etc. If I am reducing the total energy consumption, is another reward. So it's different rewards that allows us to find the optimal trajectory. Okay. Here is a scheme of our network where we have an actor and a critic. So for each step, we are going to evaluate what is the state of our system, of the observation space, that is not only limited. So the drone in reality doesn't know what is happening around, but only in some directions we're using a ray tracing algorithm that says, for each position around the drone, I know the velocity of the field. This is only for the only information. So I don't know where is the obstacle, but I'm taking the information about the distance from the obstacle step by step. Okay. Here are two cases where the drones, starting from in front of the first obstacle, is reaching this area, that is the target area. But what we can see is that, do you remember what are the most dangerous areas that we intuitively defined using the flow field and the stresses are here inside, between, and at the top of the obstacle. So the drones just avoid these areas, these recirculation areas, because they are considered dangerous. So if we consider the analysis of the flow field and compare what we have here, it's easy to understand that the analysis of the flow field is not barely a numerical curiosity, but also can help to the decision making without knowing a priori what is the best trajectory of the drone. So here we have two examples. We follow we avoid the circulation area and go direct to the target. In terms of rewards and episodes, the PPO plus LSTM algorithm outperforms the state of art if we compare the red line with the other two, where we have the 3D3 methodology and PPO. This means that to train our model, we only use it a few episodes, and we obtain a better results in terms of rewards that we want to obtain. 1 minute. Yeah. These are the conclusions. So, I practiced a lot. So basically, we studied the flow field in a human environment using a very, very expensive method as a DNS. But the main advantage was that we can a priori predict what are the most dangerous and risky areas, so that we can compare with the prediction of the deep reinforcement learning using PPO and LSTM algorithm. This is done for very, very simple configuration. What are the next steps? So the 3D case, because in this case we followed only the symmetric plane, but the 3D case is add many complexity because you have 3 components of the velocity, and the flow field is more complicated. And another step is just to consider a real case scenario that at the moment is not has not been implemented. So thank you very much.
Thank you, Gerardo. Are there any questions? Bottom.
I have one question about the algorithm. I saw that you have different terms on the reward function. I wonder, how do you define the weighting of this different reward? Is there any priority between different terms, or? For the rewards, you mean? Reward. Okay. Yes. We have different weight of the rewards because in this case we want to reach the target in the less possible time. So this means that the maximum reward is given by the step. So if we are reducing the distance to the target, the reward is higher than when avoiding some vortexes, because we accept the risk of crossing the most dangerous areas, but reaching very fast the target. Obviously, this is the objective of this algorithm. But if we also modify the weight of these rewards, the optimal trajectory found is almost the same. So I agree that there are orders in terms of importance of the rewards, but for how long as we know. Just modify a little bit the parameters is not affecting so much the code. So, like finding the optimal weights is not easy, is it?
Yeah. Federica trained a lot the code. You need to consider that in this code is missing the noise emission. This means that we have a new parameter that needs to be trained and also optimized regarding the noise emission. And so in this case, you are step by step, you have the noise at the bottom,
at the pedestrian level, and in this case, you want to use also this parameter in your optimized report.